Hello everyone, welcome to my class. Today we are covering more operational properties for Laplace transform. Let me recall, in our last classes we studied two translation theorems for Laplace transform. The first translation theorem is translation on the s-axis, and the second translation theorem is translation on t-axis. So in the first translation theorem, we transform capital F of s to capital F s minus a, multiplying the signals little ft by e to the power at. And in the second translation theorem, we delay the time t to t minus a by multiplying transformed by e to the power negative as. So now in this lecture we study derivative of a transform, convolution, and Laplace transform of an integral. Let me scroll down. First, let me talk about a derivative of a Laplace transform. Recall that Laplace transform of little f of t is denoted and defined by capital F of s equals to improper integrals 0 to infinity of e to the power negative st times little ft dt. So now let's start taking the derivatives of the transform. So d over ds of capital F of s equals to, by definitions, d over ds of this improper integral 0 to infinity e to the power negative st times little ft dt. Switch these two operations. So integral 0 to infinity. Now partial derivative with respect to s of e to the power negative st little ft dt. The partial derivative with respect to s, so the function of t is constant. So the next step, 0 to infinity, e to the power negative st times negative t times ft dt. This is the partial derivative of e to the power negative st with respect to s. This is simply the Laplace transform of negative t times little ft. So we found Laplace transform of t times little ft equals to minus derivative of the transform. Let me scroll down. Now in general, the Laplace transform of t to the power n times little ft equals to minus 1 to the power n. So if n is even or odd, we will get minus or plus. So minus 1 to the power n times capital F of nth derivative of s. Great. So now let's do some example. Let me scroll down. Yeah. So find the Laplace transform of t times e to the power negative 3t. So let's start the solution. Think as this is the transform little t times little ft. So think of this function as t times little ft, where little ft is e to the power negative 3t. Find out its transform. The Laplace transform of e to the power negative 3t is 1 over s plus 3. And then the t in front, this suggests us take the derivative. So multiply by negative 1 and take the derivative of this transform, which is, I took here, so minus minus plus, so 1 over s plus 3 square. So we found the Laplace transform of t times e to the power negative 3t equals to 1 over s plus 3 outside square. Great. Let me scroll down. 2. Find the Laplace transform of t times sine 2t. Solution. So our little ft is sine 2t. Find this Laplace transform, which is by referring the table 2 over s square plus 4. Then this t suggests us multiply by negative and take the derivative of this transform, which is here. So the derivatives simplify which gives us 4s over s square plus 4 outside square. Great. Let's move on. That's better. Part C. Find the Laplace transform of t times e to the power negative 3t times cosine 3t. So here little ft is e to the power negative 3t times cosine 3t. Then use a first translation theorem. So then f of s minus a, where a is negative 3 here, this equals to s plus 3 over s plus 3 square plus 9. So here the cosine 3t, the Laplace transform of cosine 3t is s over s square plus 9. Then we're multiplying by e to the power negative 3t, so that means we need to put a shift, so shift by negative 3, so s plus 3 over s plus 3 square plus 9. Great. And then the t in front suggests us multiply this transform by negative 1 and take the derivative. So I multiply by 1, take the derivatives, and use your quotient rule and simplify. So this gives us the final answer, s plus 3 outside square plus 9 over s plus 3 square plus 9 outside square. Great. Now let's move on. There are two useful formula. Refer the Laplace transform table, which is the Laplace transform of t times sine kt. I forget to put the Laplace notations here. So Laplace transform of t times sine kt is 2 times ks all over s square plus k square outside square. Similarly, the Laplace transform of t times cosine kt equals to, again I forgot to put the Laplace notations here, the operator here, s square minus k square over s square plus k square outside square, and b sine kt minus k times t times cosine kt. Laplace transform of this left hand side is 2k cubed over s square plus k square outside square. Great. So let me scroll down. Example 2. That's better. Use Laplace transform to solve initial value problem. Y double prime plus 9y equals to cosine 3t with initial conditions y 0 equals to 2, y prime 0 equals to 5. So let's start the solutions. Take the Laplace transforms both sides. So Laplace transform of y double prime is this expression plus 9 times Laplace transform of little y is capital Y of s equals to Laplace transform of cosine 3t is s over s square plus 9. Put initial conditions and then simplify, factor the capital Y s outside and take other term to the right side. So here capital Y of s outside, so s square comes from here plus 9 comes from there equals to, this is 2s, this is minus 5 goes to the right side becomes plus 5 plus s over s square plus 9 as it is. Let me scroll down. Yep, that's better here. So then divide both sides by s square plus 9. So capital Y of s equals to 2s over s square plus 9 plus 5 over s square plus 9 plus s over s square plus 9 outside square. So let's manipulate in the next step. So 2 times s over s square plus 9. So we can use the Laplace transform table to find the inverse for this term. We don't need to manipulate. For the second term, we need to multiply by 3 and divide by 3. In the third, for the third terms, we multiply by 6, divide by 6. This 6 is 2k in our formula here. What I showed here. Let me scroll up. Yeah, this is the 2k. I need 2 times k. So what is here, or what's k is here, I multiply by 2. So here our k is 3, so multiply by 2, 6. That's why I multiply by 6 and divide by 6. So then take Laplace transform. So the left hand side is little yt equals to inverse Laplace transform of s of s square plus 9 is cosine 3t, 2 as it is, plus 5 third. Inverse Laplace transform of 3 over s square plus 9 becomes sine 3t, plus 1 6. Laplace transform, inverse Laplace transform of 6s over s square plus 9 outside is square becomes t times sine 3t. Great. Now let's move on. Let's talk about the convolutions. So the definition: the convolutions of two signals, little f and little z, is denoted and defined by f convolution g t. So that's a star. So f convolution g equals to, defined as integral 0 to t little f tau g t minus tau d tau, or integral 0 to t f of t minus tau g tau d tau, which is commutative. So f convolution g is same as g convolution f. So let's do some quick example of computing the convolutions. Yes, let's find the convolutions of t and t square, which is denoted by t convolutions t square equals to, defined by the integral 0 to t for the first function t minus tau, second function simply tau square d tau, equals to 0 to t. Then let's foil this one, t times tau square minus tau cubed d tau. With respect to d tau integral, t is constant, so the integral of t times tau square with respect to d tau is t times tau cubed over 3 minus similarly tau to the power 4 over 4, limit tau equals to 0 to t. Put tau equals to t, so this gives us t to the power 4 over 3 minus t to the power 4 over 4. Simplifying gives us t to the power 4 over 12. Next, let's talk about Laplace transform of the convolution. So the Laplace transform of little f convolution little z equals to the product of their Laplace transforms. So the Laplace transform converts the convolution to the multiplications in S domain, in transform domain. Equivalently, inverse Laplace transform of capital F of S times capital G of S equals to convolution of signals little ft and little zt. Great. So now let's compute the convolutions in example 4. First, compute the convolutions of given two signals, e to the power negative t and e to the t, and find, in part B, find the Laplace transform of their convolutions. So as example 3, let's compute the convolutions in part A. So this is by definitions. Little f convolution little z equals to integral 0 to t f little f of tau little g of t minus tau d tau. So then integral 0 to t e to the power negative tau times e to the power t minus tau d tau. Take e to the t outside the integrals with respect to d tau, so e to the t times integral 0 to t e to the power minus 2 tau d tau. Take the integrals and put the limit and simplify. It gives us our final answer is e to the t over 2 minus e to the power minus t over 2. Then in the part B, let's take the Laplace transform of these convolutions, which is same as saying Laplace transform of this final result, which is here. Then we know the Laplace transform is linear operator, so send this Laplace transform to each of the terms. So we know 1/2 outside, Laplace transform of e to the t is 1 over s minus 1 minus 1/2 as it is, Laplace transform of e to the power negative t becomes 1 over s plus 1. Simplifying gives us 1 over s squared plus 1. Great. Or just use these theorems. Laplace transform of convolutions equals to the multiplications of their respective transforms. So then, or we can use this convolutions idea. So Laplace transform of these convolutions equals to the multiplication of their Laplace transforms. So Laplace transform of e to the power negative t times Laplace transform of e to the t. We know the Laplace transform of e to the power negative t is 1 over s plus 1 times Laplace transform of e to the t is 1 over s minus 1. Multiply, it gives the same answer, 1 over s squared minus 1. Great. Let's move on. So at this time we can ask the questions, what convolutions can do for us? The answer is, the convolution is an alternative method to find inverse Laplace transform, and later we will use convolutions to solve the integral differential equations. Let's do first example. Example 5, application of convolution. Let me scroll down. That's good. Compute the inverse Laplace transform of 1 over s times s squared plus 1. So first let's do using convolutions. Second, let's do using partial fractions. So first, using convolutions. So the inverse Laplace transform of 1 over s times s squared plus 1 is the inverse Laplace transform of 1 over s, convolutions, inverse Laplace transform of 1 over s squared plus 1. This is by definition. Let me scroll up. Here, inverse Laplace transform of this product goes to the convolution of their respective signals. Let me scroll down. Here. Then inverse Laplace transform of 1 over s is 1. Inverse Laplace transform of 1 over s squared plus 1 is sine t. So we have the convolutions. Then by the definition of convolution, this is simply the integral 0 to t sine tau d tau. The integration of sine tau with respect to d tau is negative cosine tau. Tau goes from 0 to t. With tau equals to t minus tau equals 0, it gives us 1 minus cosine t. So the alternative methods means that's a partial fraction method. We did this one in our previous sections. Let's use partial fraction method. So 1 over s times s squared plus 1 equals to, so a over linear factor plus linear factor over quadratic factor, and solve for a, b, c. The a, we got a equals to 1, we got to b equals to negative 1, we got c equals to 0. You can check quickly this one. If you check quickly, this equals to this one. Yeah. So s squared plus 1 goes here, minus s squared goes there, s squared cancel, so 1 over s times s squared plus 1. So then take inverse Laplace transform. So we got the same answer. Great. Let's move on. Now let's talk about Laplace transform of an integral. So the formula, Laplace transform of integral of little f of tau d tau, integral over 0 to t equals to, we divide the Laplace transform of little f of t by s. So the answer is 1 over s times capital F of s. This is the same thing here on this diagram. The Laplace transform of little ft is capital F of s. Laplace transform of an integral over 0 to t of little f tau d tau is 1 over s. Laplace transform of little ft. So quick proof, left hand side, which is just by the definition, this is simply the Laplace transform of these convolutions, and the Laplace transform sends the convolution to the product of the transform. So Laplace transform 1 is 1 over s times Laplace transform little ft is capital F of s. Great. Let's move on. solve the integral differential equations. Little yt equals to 1 plus 2 times the integral over 0 to t of e minus e to the power minus 2 times t minus tau times little y tau d tau. This integral is by definition the convolution of e to the power negative 2t and yt. Excuse me. So then take Laplace transform. Laplace transform 1 is 1 over s plus 2 as it is. Laplace transform of e to the power negative 2t convolutions yt equals to the product of their Laplace transform. So Laplace transform of e to the power negative 2t becomes 1 over s plus 2, and Laplace transform of e little yt is capital Y of s. Solve for capital Y of s. So bring this guy to the left side and factor out capital Y of s. Then next step, capital Ys of 1 minus 2 over s plus 2 equals to this 1 over s on the right side. Then solve for capital Y of s, which gives us capital Y of s equals to s plus 2 over s square. Use partial fractions in the next step. So capital Y of s equals to, it turned out to be 1 over s plus 2 over s square. Let me scroll down. Then in the next step, take the inverse Laplace transform. So little yt equals to inverse Laplace transform of 1 over s is simply 1, plus inverse Laplace transform of 2 over s squared is 2 times t. So we got the answer. Great. Let's move on. Next, let's talk about LR series circuit. The Kirchhoff's second law says sum of the voltage drops across an inductor, resistor, and capacitor is equals to the impressed voltage. So this gives us L little I prime plus R I plus 1 over C integrals 0 to t I tau d tau equals to capital ET, where L, R, C are the constant. We call this equation as an integral differential equations, and we need to solve these equations to find the current little I t. So let's do example 7. Solve little I prime plus 10 times I plus 125 integrals over 0 to t of I tau d tau equals to 110 with initial conditions I0 equals to 0. Take Laplace transforms. So Laplace transform of little I prime is this term inside the bracket plus 10. Laplace transform of little I is capital IFS plus 125, and this by the convolutions. This is simply the convolutions 1 and little I. So the Laplace transform of this integral gives us the product of their Laplace transform. So Laplace transform 1 is 1 over s times Laplace transform little I tau is simply capital I s equals to Laplace transform of 110 is 110 over s. Multiply by s, put initial conditions, simplify, this gives us this expressions. Then take capital IFS, factor out, then s square plus 10s plus 125 equals to 110. Let me scroll down. Then use completing this square. So s square plus 10s plus 125 equals to s plus 5 square plus 100 times capital IS equals to 110. Divide both sides by this coefficient of capital IS, which is here. So capital IS equals to, I break 110 to 11 times 10 over s plus 5 square plus 100. Then let's take the inverse Laplace transform. First unshift. The unshifted form is 11 times 10 over s square plus 10 square. Then the inverse Laplace transform of, don't worry about this constant 11 as it is, inverse Laplace transform of 10 over s square plus 10 square is simply sine of 10t, then modified by this 5, means multiply by e to the power negative 5t to this signals. So our final answer is then the current equals to 11 times e to the power negative 5t times sine 10t. Great. So we finish these sections. In the next class we will study the Dirac delta functions, which is denoted by delta. Thank you.